All right, well, it is my pleasure to introduce Liz Arnold from Department of Mathematics at Montana State University and Beth Burroughs from Department of Pathology, Microbiology, and Immunology from Vanderbilt University, presenting using physical simulations to engage students in SIR model of the spread of an infectious disease.
Thank you, Gavin, and welcome everyone. And thank you for coming and taking part of your Saturday to join us today. And today, on behalf of my colleagues and I'm going to share two physical simulations that we have done both at the K-12 level and the undergraduate level about motivating models of spreads of infectious diseases. And so I want to quickly acknowledge my awesome and amazing collaborators. So Beth Burroughs is currently online. So if you have any questions during the talk, feel free to type them in the chat and she can kind of monitor the chat and respond. And Owen Burroughs, I want to give a special shout out to. He is our graduate student that is not in the Department of Mathematics. And what I personally really love about mathematical modeling is the interdisciplinary nature. And Owen has opened my eyes to this whole biology behind the spread of a disease that has made my own understanding of the mathematical model of a spread of an infectious disease even more powerful. And then Mary Alice Carlson has done a lot of work with middle school students and using the simulations to motivate again the need for a mathematical model to model how infectious disease spreads. Cool. So just in a nutshell, the process of mathematical modeling includes creating these mathematical representations that we as modelers use to understand and make decisions about the world. But these mathematical representations are very abstract. There's a lot of variables, parameters, different types of equations, which makes it really challenging for our students to fully conceptually understand all the different components of these models and these mathematical representations. So something myself and my team have been really thinking a lot about is how can we help support our undergraduate students, our K-12 students in really understanding everything that goes into the mathematical representation of their model. And when we started to think about this, we really relied on what educational psychologists have kind of said over the years, that it is helpful to take some concrete experience and use that to transition to this abstract representation. And in mathematical modeling, all the problems that we do are really based on some kind of experience. And so we started to think about, in the context of the spread of a disease, how can we provide safe, concrete experiences that will help students start to understand the mathematical representation of everything that goes on in the spread of a disease? And so with this kind of background, the example that I'm going to share is the SIR model in particular. And we have used this in two undergraduate mathematics courses, a general differential equations course, and then a mathematical modeling specific course. But again, like I said, these simulations really originated in a K-12 setting. And so as you think about these simulations, they really can be adapted to kind of any situation that you have. So just briefly, I want to kind of go over an SIR model. You begin with a population of n individuals, and we compartmentalize all of the population into one of three states: whether or not you're susceptible to an infectious disease, whether or not you're infected to that disease, and whether or not you have recovered to that disease. And so some of the assumptions of the SIR model is the disease is typically of short duration and it's rarely fatal. The disease spreads through contact between individuals, so you need to have some contact with an infected individual to have an opportunity or have a chance, I guess, of getting the disease. And then the individuals who have recovered from the disease remain immune. So these are some of the basic assumptions of the more simplistic SIR model. And one thing that we think about is, how do we transition from susceptible to infectious, infectious to recovered? And this is where all the biology comes into play. So mathematically, I can represent these transitions from susceptible to infectious, infectious to recovered with some parameters, beta and gamma, but there is a whole lot going on behind the scenes. And that is what the mathematical representation does not show. What is all of the biological processes that are involved in that? And what I really like about the SIR model, especially in the context of differential equations, is we can write this SIR model as a system of three ordinary differential equations. And there's really only two parameters that we need to worry about. So it can become much more complex, but the SIR model I feel like is very simple and a good introduction to a system of differential equations. And then of course you see in this graph, I think these graphs became very popular during the COVID era of we can get numerical solutions to this system of differential equations. Okay. So like I said, I really value the SIR model because it's very popular for its simplicity, but also it's very popular for the possibilities to expand upon this SIR model. When we have thought about how our students understand the SIR model, some of the things that we have found is that whether or not you become infected, it really occurs at this individual level. But we use the SIR model to make predictions of infection at a population level. And so there's this kind of like disconnect with our students of this individual level is the infection, but we're really predicting it at a population level. So we really have started to think about how can we help kind of bridge that connection. And then, like I've been saying, there's a lot that goes into whether or not you get infected with a disease. And so the beta and gamma mask some of the very complex processes that are behind the spread of an infectious disease. So all of this is to motivate how can we give our students safe, concrete experiences that help them understand all of these complexities in the SIR model. So we have used two physical simulations that I'm going to talk about today. And the goal of these physical simulations is to, again, help transition from a concrete experience to that abstract mathematical representation of the SIR model. And we really wanted these simulations to be fun, active, get out of your seat, and elicit students' mathematical curiosities, as well as like the biological curiosities. So combining the math and the biology that goes into a model of the spread of an infectious disease. And then we really want our students to engage in the process of modeling. And so these physical simulations give students an opportunity to ask questions about what factors influence disease spread. And so these simulations give students an opportunity to ask mathematical questions, which is part of the modeling process. So there are two simulations that I'm going to talk about. One is an acid-based simulation, and then one is a probability-based simulation. And I'm going to start with the acid-based simulation. And we do both of these simulations in a 75-minute class period, and we always start with the acid-based simulation. It takes about 30 minutes. It works pretty well with a group of 25 or more, but we've really had success with as few as like 10 students. This simulation incorporates exchanging solution from cups, and we use 3 rounds of this simulation. And we really want our students to experience the importance of dosage and the human interactions in the spread of the disease. And so the materials you need for this acid-based simulation, you can get in your department's chemistry department, or what I have done and Beth has done is we have just gone to Home Depot and gathered these materials. And so it works really well if you get a lot of clear plastic water cups. You want something, if possible, to transfer some solution from one cup to the other cup. And so we've used pipettes. Otherwise, we've just kind of poured some liquid in from cup to cup. If you can get acetic acid or vinegar, and then baking soda, and then phenol red, which you can get from your chemistry department or go to the spa aisle in Home Depot or a home improvement store. If you can't get that, pH strips also do work. So these are just the materials that you need. And so here is round 1. So we consider round 1 of this simulation as having no intervention. And so what we do as instructors, and I'm just going to hypothetically say we have 30 students in our class. We get 30 clear plastic cups and we fill them up with water. And then we determine how many of those cups we want to become infected. And what we do is we replace about 20% of the water in those cups with vinegar. So vinegar is going to be the infection. And then we give each student a cup and we don't tell them whether or not they are infected or not. And we've done this in a couple of ways. And the way that I have found works really well is I just label each cup with a number 1 through 30, and then I write down which ones I replace some water solution with vinegar. And then what we do is all the students come up, they grab a cup, they go back to their seat, and then we ask them to get up and just mingle with each other, go talk to each other. And you can make this fun of like, well, what did you do over the weekend? Or we've also had them talk about homework problems. And when they meet with someone, as you see in this picture, they take their pipette and they exchange some solution in their cup to their partner's cup. So we repeat this, and we repeat this, I don't know, a couple of minutes until you think there's been enough like saturation, mingling interactions among your entire class. And then what we do is we ask students to kind of go back to their seat and we say, do you think you're infected? Why or why not? And so there's that individual kind of aspect. And then we ask them, well, how many in the class do you think are infected? So there's that population level. And then this is a fun part is we reveal who was initially infected. So we'll say, oh, cup number 5 was infected and cup number 10. And this is where you hear a lot of groans from students saying like, oh no, now I'm going to be definitely infected because I talked to Charlotte who was infected. And so we reveal who was infected to begin with, the patient 0, and then we ask them to revisit their predictions and why or why not they changed. And that's where discussion about interactions kind of comes into play. My favorite part of this activity is using the phenol red. And then, so after the students make predictions of whether or not they are infected, we as instructors take the phenol red and we go around individually and we just drop a couple of drops of the phenol red into their cup. And then the cups change color based on whether or not they're infected. And this is a highlight because then everyone gets to see who is infected and who is not, like live on the spot. And so that's why we recommend the clear water cups. So this is just a great fun activity. And then what we do, that was round 1 with no intervention. But when we think about modeling, we say, well, how can we make this model or this simulation better? And so round 2 is we decide as a class a non-vaccine intervention. So again, we're engaging our students in the modeling process where they're making decisions that they want to simulate. And some ideas that students have is to create social pods. And so then you could separate the class into groups and they can only talk within their group. My favorite has been students coming up with masking, and they said that we should get coffee filters and they should put the coffee filter over their cup. So when students transfer the solution, not as much gets into their cup. And then we've also done contact tracing and quarantine. So we've repeated the round like I described the first time. And then after a minute, we say, hey, so-and-so was infected. If you talked with so-and-so, you all need to go to this side of the room. And then everyone else continues to mingle as normal. So in all of these rounds, we prepare the cups before we get to class and so that they're just ready for students to pick up. So with this round 2, with the non-vaccine intervention, you create the cups in the exact same way you did before. You replace some with some vinegar for infected, and then you do this non-vaccine intervention with the simulation. You do the whole thing again of asking students if they're infected, and then you go around with the phenol red and see who is infected and whatnot. Round 3 is, again, how can we improve this model? Well, we can include some kind of vaccine. And this is where the baking soda comes into play. And this is where Owen, the biology specialist, knows all of the biology behind this. But the baking soda and the vaccine counteract. So the baking soda serves as immunity. And so if someone transfers some vaccine into a cup with baking soda, that baking soda will still remain not infected. So you prepare the cups in the exact same way. Again, some have vinegar for infected. And this time you also determine how many of the class you want to be vaccinated. Again, this could be about 10% of the class, and you can change this as you like. And what you do in those cups is you put a couple teaspoons of baking soda in there. And this is also why I say it's a good recommendation to make these cups before class, because when you put baking soda, you can sometimes see the residue. So if you make it ahead of class time, it gets a chance for the baking soda to settle. So it's not as obvious that there's something in the cup. So again, we repeat the whole simulation. The students mingle. We ask, do you think you're infected? We reveal who's infected. And we have a discussion after all of this. So after 3 rounds, this is where we ask the students to discuss their concrete experiences with the spread of an infectious disease and maybe how it might relate to the mathematical representation that they will see a little bit later. And so with this first simulation, we ask them specifically what factors influence whether or not an infected individual transmitted an infection. And this is where students start to come up with these ideas. They say, well, it depends on the number of interactions that I had. And so they're really getting at kind of a component of the SIR model and the interaction between susceptible and infected. They talk about the likelihood of transmitting a disease if you were infected. And this is where you can talk about in this simulation that likelihood is close to 1, because if you transfer some vinegar, you're going to become infected. And then one of my favorite parts is the students start to talk about the amount of solution that's transferred between individuals. So really getting at this dosage kind of effect. And they love to line up all of their cups at the end based on like the clarity of infection, the clarity of not infected. And then you can kind of see in this picture in the middle, there's some that are like a color between yellow and pink. And so this leads to a great discussion of the biological processes behind dosage and infection. So then we also ask them again in modeling, like, well, how can we make this model better? So we asked them to describe some of the limitations of this simulation, what's missing. And some things that have come up, students discuss this lack of stochastic behavior, that if they come in contact with someone that's infected, they're automatically going to get infected. But that's not the reality of how infections spread. They also talk about how the vaccine, the baking soda, is transferred. And you kind of see that in like the previous picture in that middle, like between pink and yellow color. And that's not typically the case with a lot of diseases. You can't, or a lot of vaccines, you can't transfer the vaccine from person to person. And then another big thing they noticed in this simulation is nobody recovered. You were either susceptible or you were infected and you remain infected. And so we use these ideas to kind of segue into the next simulation. And so the next simulation is the probability-based simulation. And you'll notice in that first simulation, there was no data that we collected. We just wanted the students up and moving. But this time in the probability-based simulation, we have a data sheet that we want students to use and collect data about their individual status. And so this simulation is based on the game rock, paper, scissors. Again, it takes about 30 minutes. It works well with 25 or more, but we've had success with fewer. This simulation really incorporates the random movement, and it involves all 3 states of the SIR model: susceptible, infected, and recovered. And we really hope the experience that students take away from this is that there's some probability of being exposed to an infected individual. And if you are exposed to that infected individual, there is a probability of becoming infected. So for this simulation, your students need to know how to play rock, paper, scissors. It's fun to bring some music, and we have a data sheet, which I'll show you. And then you need, as an instructor, a way to compile all of their individual data to share with the class. So here's the example of the data sheet that I was talking about. And we as instructors create these data sheets. So we decide, again, maybe it's about 10% of the class is going to be infected. And so we write S or I at time step 0, and then we just randomly pass these out to the class and ask them to keep the status of the status that they're in to themselves. And then this, again, we're engaging students in modeling, and we have the students come up and decide how they're going to model the behavior of the spread of a disease with this simulation. And so some of the things that the students need to think about are how long does someone remain infected? And you'll see in this data sheet here, this class decided that someone remains infected for 7 days, and then after which they now become recovered. So they need to think about the duration of infection, but then they also need to decide, well, once you have recovered, are you immune? Or can you get can you become infected again? So these are all decisions that modelers make. These are all the assumptions that they're making that go into their model. And then they also need to talk about, well, what's the outcome of playing rock, paper, scissors with someone? And typically what the class decides is that if a susceptible person plays rock, paper, scissors against an infected person and loses, then they have now become infected. So what we do is we ask students, we give them this data sheet, and what we do is we play music. And so the music is in kind of incorporating this randomness. We say they can dance or just walk around, and then it's kind of like musical chairs. And then after, I don't know, 10, 15 seconds, we stop the music and they have to go to the nearest person and play rock, paper, scissors with them. And then after they play rock, paper, scissors, they reveal their status and then they update their status of whether or not they're susceptible, infected, or recovered at each time step. And we repeat this until students have recorded about 15 to 20 time steps. Okay. So after they do this, we really invite students to, again, share experiences about their individual data set before we move on to the population. So here we have noticed when we talk about how their concrete experience relates to the parameter values in an SIR model, this simulation really helps them think about the probability of getting sick when infected. In this case, there's a 1 in 3 chance. And there's this probability through the random movements of being exposed to an infected individual. And this simulation also allows us to ask our students, well, what factors influenced recovery from recovery from the disease? So after this, this is where the instructor compiles all of the individual data, and we have just kind of given this data set to our class and said, well, how do you make sense of now this population? Like we have all this data from the population of our class. What do you want to do with it? And what this kind of leads next to is the next steps, that transition piece to the abstract representation. And we've done quite a few things. And so the class has used their population level data and created a numerical simulation where they replicated the rock, paper, scissors simulation, and they've used their program of choice. And then we've also kind of started to derive and introduce the SIR model. So prior to these simulations, we never put up the SIR model at the beginning. We always put it at the end where the students can then take their concrete experiences and make connections back to the mathematical representation. And so what we have found is students love this. I've never had students leave not smiling after doing these simulations. It's just fun to get up and walk around in a math class. But the concrete experience of these simulations really evokes students' curiosities, their mathematical curiosity and their biological curiosities. And that helped them make connections between the simulations and what they experienced to, again, like the parameter values of the SIR model, why it's a system of differential equations and all of the components of the differential equations, and really what those parameters actually mean. And so through this experience, they experience some of the complexity and the biological processes behind disease spread. And what was really exciting is students began to pose their own mathematical questions. So when we had these discussions, students started to ask questions that I, as an instructor, could say, that's an awesome question. And how can we answer that? We can answer that with an SIR model using differential equations. So it really motivated the use of differential equations. These is what we found. So I thank you all for joining again on a Saturday and listening. My colleagues and I, we wrote this paper it was a special issue of a Simioid. And so there are more details in this paper about all of these simulations. And I am happy to provide any info that you need if you send me or my colleagues any kind of email. So with that, I'll take any questions in this last minute, but thank you again.